First, let's take a conductor. Bend it into a U shape and allow it to pivot in the center. This is our armature. Now let's attach a split copper ring to the ends of the conductor. This is called a commutator. On each side of the armature, we'll place a magnet so that the North Pole is on one side and the South Pole on the other. This is known as the field. We will also need two brushes that can slide easily over the commutator to provide the armature with electrical current. Now let's connect the motor to a battery and see how it works. As current flows through the armature, the magnetic flux lines interact with the flux lines of the field. Because the armature is U-shaped, the lines are clockwise on one side and counterclockwise on the other. This produces opposite magnetic fields. The armature will then rotate in one continuous movement as its magnetic fields interact. As the armature rotates to a position perpendicular or 90 degrees from the field, it is in the neutral plane, where the interaction of the magnetic fields is balanced. At this point, the current to the armature is cut because of the commutator's action, and the armature coasts to the opposite side of the field. The commutator once again connects the current to the armature, and the rotary motion continues. Although the current flow does not change directions, it is sent to the opposite side of the armature. The flux lines of the armature and the field work together almost like a lever to produce a twisting motion in the armature. The twisting or rotary movement is known as torque. The amount of torque produced is dependent on the strength of the current, the distance between the field and the armature, and the type and number of windings. This simple motor would not do any practical work. It would have a problem starting unless the armature always stopped parallel to the field. If it stopped in the neutral plane, the armature and field flux lines would be balanced and no torque would be produced. Practical motors use multiple loops in the armature. By adding loops, the motor becomes self-starting because there is always some segment of the armature interacting with the field. As one loop approaches the neutral plane, the commutator switches current to another segment, thus ensuring a steady and continuous production of torque. Automotive starter motors may have more than 12 loops. To be truly efficient, electric motor armatures are generally wound so that multiple segments are interacting within the field, thus producing a continuous and smooth rotation.